Hi, everybody. Day 3. And if you're hearing this today, it's either Friday or Monday. But if it's Friday, we got the weekend coming up. We're finishing up 4.2 today on our lesson. We've done 4.1. It's all about what is work. We did the first part of 4.2. What does a machine do to make work? It changes how much force that gets exerted into the machine. It changes the distance in which your force is exerted, or it changes the direction. All three of which are really, really beneficial for you, and that's why we use machines. Today's lesson is going to be about mechanical advantage and efficiency. You're going to see a lot where I use MA. That's just shorthand for mechanical advantage. I don't have an equation written here. It was not liking how the formatting of it went in, so I'll just talk to you when we get to parts like that. But we got number 7 through 11 today. And, the first thing, it's all about mechanical advantage. What a machine does is it takes the force that you exert and it multiplies it through the machine. The example I kept bringing up in our last video was like a can opener. If you have a can opener, and let's say that you have an input force of 1, and then the machine has an output force of 2.5. So we'll use 2.5 this time. Going from 1 to 2.5, it's multiplied 2.5 times. So the mechanical advantage of this machine would be 2.5. And that's a good advantage. Usually anytime you have more than 1, it's going to be beneficial for you to use. The equation for mechanical advantage, you're going to take the output force and you'll divide it by the input force, and you'll just get a lone number. Like if it's output force of 2.5, input force of 1, 2.5 over 1, it's 2.5. That's quality machine. For machines that multiply force, mechanical advantage, we are hoping is greater than 1. For the other ones, it may not be above 1, and it's really based on the type of machine that we're using. For this one that's multiplying force, here's an example. Can opener, you exert 20 newtons. The can opener exerts 60 newtons. If we calculate this, output divided by input, 60 divided by 20, your MA would be 3. That's a good mechanical advantage. If we have one that's multiplying distance, output force is less than the input force. And this is an instance where it's not so bad. If you exert a force of 20 newtons on a machine, the machine exerts 10 newtons. You have 10 divided by the 20. MA is only 0.5, but it's exerting your force over a longer distance. The primo example for this one would be a ramp or an inclined plane. Rather than having to lift a super duper heavy object up a several foot wall, you can put a ramp there or use a dolly, put wheels underneath it, and push it up. So you're still going to use the same force, but you're not going to get as much work out of it, but it's going to make the job easier because it puts your force over a longer distance. The numbers don't make sense, but it is being easier for you to do. It's exerted over a longer distance. If only direction changes, input and outputs are equal to each other, so MA is 1. For one that changes direction, an example would be a pulley system. You pull down on the rope for the pulley, an object gets pulled upwards. If there's just one pulley that's being used, your mechanical advantage is going to be 1. If I find an image of this, which I am right now, ooh, yeah, this is what we want. Here, well, maybe I can't record this or share it with you. But if you have one gear inside of the pulley system, your mechanical advantage will be 1 because it's multiplied once per gear. If you put 2 gears in it, your mechanical advantage, it's being multiplied for each of the gears going through there. So you put 2 in there, it's going to multiply your force by 2. You put 5 of them in there, it's going to multiply your force by 5. So you're going to end up with the more mechanical advantage, the more pulleys you use in that system. Ideal situations. An ideal situation is the perfect scenario. If you have a perfect scenario, input and output work are going to be equal to each other. That's not how the world works, though. But this is saying that if you put in some work into a machine, the machine is going to put out the exact same amount of work. But input force is always less than the output work. Losses are usually due to heat or friction. These are two big things that are going to, friction. You're going to lose a lot of work just by overcoming of the friction. If you have less friction, output and input are very close to each other. That's good. If we want to compare these, so we want output and input to be similar. In order to do that, you'll do a calculation for efficiency. The equation? Not in there. Okay. So to do the equation for efficiency, you're going to take the output work and you're going to divide it by the input work, and you'll multiply that by 100 and it'll give you a percent. So if the output work, now I mixed that up. It's input divided by output. So whatever you put into it divided by, no, I was right the first time. Output divided by input, yeah. So how much you're getting out of it divided by how much you're putting in it times 100. Ideal machines have an efficiency of 100%, which would be ideal, but very, very, very rare and probably not possible. Something that you would use where you might understand the efficiency best is your car. The engine of a car is not very efficient. It's only about 30 to 40% efficient, meaning that of the fuel that you put in your car, only about 30 to 40% of that fuel is used for purposes of the car. So driving, heating your car, cooling off your car, basic functions of the vehicle. The rest of that, the 60%, is being lost by heat. Think of it this way. Don't do this, but had you let your car run for a little while, and then you go outside and you touch the hood of it, it's going to be very warm. That is where most of your heat's being lost. A lot of it's being given off as heat. So if you touched the hood, it's going to feel very hot. Now, don't do this because it's not going to feel good. Had you had a engine in your car that was 100% efficient and you let your car run for a while and then you go outside and touch the hood, you would feel no heat. It would be the exact same temperature as the air surrounding. And that's just awesome. But it's never going to happen. We were just naturally going to lose a lot of ours to heat. That's just what's going to happen. Two types of mechanical advantage. There's AMA and IMA. There's actual and ideal. Ideal mechanical advantage would measure the perfect amount of mechanical advantage that's possible. So if there's no losses due to friction, to heat, or to any other factors. AMA is actual mechanical advantage. It's what you get in a real scenario. So this is what you would get if by doing a task with your machine. So your ideal machine would have a perfect mechanical advantage, but you're never going to get that out of it. Comparing these two, take your actual mechanical advantage, divide it by your ideal mechanical advantage, and that'll tell you what your efficiency would be as well. Efficiency can be increased. There's things that can increase your efficiency. Examples. Well, think about what we were losing work to. Think about your car. Where are you using or where are you losing a lot of the efficiency? Heat is a big one. So ways you can help with efficiency. Lessen the friction. Okay. Use newer upgraded machines. Okay. Have upkeep on whatever the machine is. Okay. The more that this is done, the better the machine is going to work. It also is usually more financially safe this way too. That is the end of 4.2, mechanical advantage and efficiency. We have a little lesson coming up real soon. Well, the lesson is done. We have a little chat coming up soon. We chat in here every day. We're going to be here every day. We have a video project today too, so we'll get to see that. And I will talk to you soon.